Does artificial intelligence have a sense of smell? Welcome to the AI show with John Koetsier. It's a bit of a different AI show. I'm interviewing somebody from Intel, but he's sheltering in place and there's no great video or perhaps network as well where he is. So I'm going to be on screen and he will be a voice, and you will have the distinct displeasure of watching me if you're watching this live stream. Well, welcome to the AI show with John Koetsier. We're talking about AI. We're talking about a lot of simple problems that AI does, right? We sort Legos with AI. We sort maybe garbage. We look for different colors or shapes or something like that. There's also some more challenging things to do, right? Intel has been building some chips, AI chips, with neuromorphic architecture. The goal is solving complex problems, real world problems, with less training than we typically give uh, AI systems in the past. So, want to welcome my friend to the show right now. Please introduce yourself.
Yeah, hi, John. I'm Mike Davies. I lead our neuromorphic research program here in Intel Labs.
Excellent, excellent. Well, thanks so much for joining us. Talk to us a little bit about what you built. You built something very, very interesting to give AI a sense of smell.
Yeah, sure. That sense of smell, this capability to learn and recognize odors, is really the one of the more recent applications that we've developed on our Loihi chip. And the chip itself is a general neural computer. You could kind of think of it as being inspired from the way the brain works at the kind of the lowest level that we have any real understanding of, which is the neurons and the connections and the temporal processing that that our brains are performing at
Yes,
continuous in real time. So
yes.
that's the chip is Loihi, and yeah, this is some research we've done in collaboration with neuroscientists over several years now, and it's just recently published.
So, talk to me about why you tackled this particular problem.
Well, it's a really interesting one from a couple different perspectives. So, in general, there's so much we don't understand about the brain, right? It's still a mystery after decades of neuroscience, science, and many intelligent people thinking deeply about it, studying it. But one area that we do understand, or relatively, is olfaction. So the sense of the circuits in our brains related to smelling. And in general, what we see is, the further out from the core cognitive parts of the brain, the cortex, as we go to the edge of the peripheral nervous system and the sensory processing, that's where we have, kind of relatively better understanding of what's going on in this mysterious black box of the brain. So it's just an area that was well understood in the sense that there were low-level neuroscience models that we could abstract to the point of being able to map them into the feature set that our Loihi chip supports. And it's also just from a machine learning perspective, it's a difficult problem that deep learning doesn't necessarily solve that well. So especially when you consider the efficiency of learning, how many samples are required to
Right.
achieve a good level of classification.
And that's typically an issue, right? I mean, needing so much big data, if not tons and tons of data, to be able to make determinations on future instances that it sees. But you found a way to make that much quicker. Is that correct?
Yeah, yeah, exactly. With the network we have, we can effectively learn with single examples. So with just showing one kind of clean presentation of an odor, kind of a 70-dimensional vectorized representation of an odor, we can store that in this high-dimensional representation in the chip, and then it allows it to then recognize um, a variety of noisy, corrupted, occluded odors like you would be faced with in the real world, where you're
Wow.
all bombarded with all kinds of different smells, and it will be able to detect at very faint corrupted levels that particular learned pattern.
That is really, really interesting. Is that somewhat analogous to how a human might learn based on seeing one image of, let's say, a tiger and being able to recognize a tiger again, or smelling an apple and recognizing that again?
Exactly, exactly. That's really what we are one of the main things we're trying to understand and map into silicon in our programming is the brain's ability to learn with single examples or very few examples, which is kind of the opposite of the deep learning tool that we have today built on backpropagation, which it can solve some incredible problems, but it requires lots and lots and lots of data, and it's learning in very slow incremental steps. And that's just different from how we intuitively think of learning. If you look at a toddler or an infant, and you present single examples, and immediately, if it's that tiger that they've seen for the first time, they'll learn it forever based
Yes.
on a few examples.
Yes.
And what's even more amazing is that they'll learn a cartoon of a tiger. They'll recognize something that looks nothing like the original input you may have presented, through this automatic process of abstraction that our brain is doing. So,
And is that analogous? And is that analogous to what you just said, where you talked about occluded samples, or samples where it's not clear what the smell is, but it's there, but there's something else with it? Is that equivalent?
exactly right. What our chip and this algorithm is doing is it's searching, the data that's presented to it for snippets, little subsets of this pattern that it recognizes, and it will suppress the noise just automatically through this very efficient parallel search process. And so it's kind of understanding the real salient important parts of that odor representation, and kind of intuitively you could think of as ignoring the parts that is just clutter and noise.
Mm-hmm. Mm-hmm. Talk to me about error rates, because one of the challenges that we have as humans is we see something, we see a specific, and we make a generalization based on that specific. So we see one example, and boom, hey, we know what reality is. Are you seeing similar things with your system?
So for this particular example that we've demonstrated and published, that's not necessarily a part of it. This is really an ingredient on the path towards that larger goal. I mean, that's really a very hard problem of AI, is to understand this kind of generalization and abstraction process. This hierarchical understanding of the constituents that together form the pattern that we recognize as the whole. So that's ongoing work, and we expect to make progress and build on this example of olfaction. But you could think of this is what we have now with this odor perception is the first layer. It's recognizing just the raw data, and now what does that mean? How does that connect to other concepts? Is this a good odor or a bad odor? Is it, if it's an apple, what type of apple is it? This kind of next level, more subtlety and generalization is something that will be future work.
Super interesting, right? I mean, you can think of in a human sort of context. Okay, I recognize the smell of apple. Now I attach to the concept of this green thing, but also maybe this red thing, other things like that. Maybe I attach to the concept of being hungry or something to eat or other things like that. Super interesting what you're building there. Can you talk a little bit about what AI technologies or techniques you used in doing this work?
Well, we are from a conventional computing perspective, it's super exotic because it doesn't look like a conventional processor, and it doesn't even look like a conventional deep learning accelerator. So in the conventional AI world, everyone speaks of multiply accumulation operators, max.
Yes.
How many max per second or per watt can you compute? And in this technology that we're using, we don't have a single Mac. We're not even using that same basic computational primitive to solve these problems. So we're taking more of a first principles perspective of rethinking computing based on what we find in the brain, you know, ignoring or forgetting everything we know about conventional ways of designing and computing chips, and instead just trying to kind of reverse engineer and understand the principles of what is the brain doing, and mapping that into silicon.
That is
So that's the
super.
basic technology. Yeah.
That is super interesting. That almost harkens back to how people tried to do AI. Researchers tried to do AI maybe a couple decades ago, really trying to, how does the brain work and map that onto silicon?
Yeah, this field, I mean, this approach is, I mean, it dates back, yeah, quite a long time. I mean, the original perceptron, this was Rosenblatt, did this and is really the inspiration for all of the deep neural networks and this artificial neural network model that's come to fruition in the past decade. That dates back to the 1950s, I believe it was, where he had an entire machine room, a whole system the size of a cabinet, which was implementing one neuron.
Yes.
So that idea has been around a long time. Um, and more recently, this approach that we're taking is dates back into the 80s with Carver Mead and work that was done at Caltech, which is taking a more modern look at what's understood from neuroscience. But still, it's that's now 3 decades ago, and we're still working on getting this to a point of commercialization where it can provide real world value. But yeah, these ideas have been around a long time. The brain, in fact, was an inspiration for John von Neumann and Alan Turing. Way back at the genesis of the computer architectures that we're using today.
Yes.
So yeah, this has always been a vision of computing, certainly.
Interesting. So, talk a little bit about some of the challenges or problems you had as you were building this. Did you come into some dead ends? What problems did you have as you were building it out?
Most of the problems we had were, I would say, the more mundane engineering types of challenges. We had the benefit of bringing a really unique design technology into this program when we started it, an asynchronous design methodology, which is different from how chips are conventionally designed. But the brain is an asynchronous machine. It doesn't have this global clock, which is present in all the conventional chips that are produced. Happens to be that my group came from a background of a startup company doing Ethernet switches with this asynchronous technology, so we had that available. But because it's so different, there's a lot of challenges in uh, building chips with a different methodology that doesn't
Hmm.
conform to the standard method. So it gets very technical in terms of the particular problems, but everything from design entry to verifying that the functionality is correct and as expected, and just conforming to all the standard quality checks that Intel would require for chips that we fab.
Yes.
So those are mainly the problems we had. Um,
Interesting. Interesting. So you've released the research. You're working on commercializing it. What's the current status? When will this be out there? And what else will it work for?
Well, the chip is, in a sense, it's out there. We have it's really restricted. It's a research chip, and we built a number of systems around this now and a whole software stack, and we made this available to a whole network of research collaborators, in academia and government, and even a number of corporate groups now. So we have about 100 groups around the world using the chip and helping to advance it and to a commercialization point. And the challenge there is really connecting the basic hardware capabilities, developing the software, the methodologies, the algorithms that then solve real world problems.
Yes.
And so that's really the challenge we're at. And almost all of our focus now is on that problem, working with all of these collaborators. I think there's good progress. There's things like this olfactory example, which we can already see some real world uses for it, and a number of other promising kind of avenues like that. So it's hard to put concrete predictions on it, but I think we're dealing with a matter of a few years, at 5 years maybe at most, before we'll
Sh-
in the real world.
Sure. What kind of sensitivity are we talking about here? I mean, are we talking dog level sensitivity? Are we talking beyond that?
It's hard to equate it to human capability because we've evaluated this on a kind of an abstract data set, which isn't calibrated in that way. But I think one general property of this is, if you and we see this in many examples in this neuromorphic domain, is as you give the network, the problem, more resources, more neurons in this case, you
Yes.
can achieve greater levels of sensitivity. So it's really a spectrum of how much how many resources, how many chips, how much memory do you throw at this problem to achieve like superhuman or less than human, depending on what the application would require.
And you can imagine a lot of applications there, right? I mean, from testing, from food safe testing to is something rotten or is it still fresh, to security applications, sensors to sniff out perhaps explosives or other things like that. I mean, what are some of the
Exactly.
applications that you've thought of?
Yeah, well, you've named two exactly right there. Measuring or detecting hazardous chemicals, in manufacturing settings, um, potentially even disease diagnosis. So there's some really intriguing research about being able to smell kind of the chemical byproducts of
Wow.
various diseases, including cancer. Just from someone's breathing, basically. So yeah, we're at Intel, we're unlikely to take a product like that to market, but we would certainly partner with others and enable those kind of applications. But there's the challenge of the sensor side of that as well, and that we see that in all many of the applications we look at, at the edge, in that the data needs to be presented in a manner that's suitable for this kind of neural processing, and that's sometimes just as hard a problem as the computation side.
Sure. It's really interesting to me because we have a lot of sensors for visual things, right? If you look at smart home or you look at smart cities, that sort of thing, you have a lot of sensors for visual data. You've got a lot of sensors for auditory data, right? I'm speaking into one right now. So are you. Everybody who's listening right now has one of those, right? You have sensors for other things like heat, particulate matter, right? I've got a sensor in my house that senses how much particulate matter is floating around in the air. But smell is one that we really haven't exploited so far, and it kind of adds to the entire picture. You can really see how that could be a part of a whole smart city, smart office, smart work, smart factory, smart home type of scenario. Correct?
Absolutely. Yeah, it's a underappreciated sense. In fact, it's really the evolutionary speaking, it's the oldest sense that's been around. I mean, the very earliest bioorganisms basically smelled. They detected chemicals, and that's what's survived all these billion years. So yeah, it's definitely, maybe its time has come, and once we have the sensing and the compute technology, it'll be a recognized first class citizen in competition with others.
Wonderful. Now, put your futurist hat on for just a second. Walk us out 3 to 5 years, something like that. Where do you see this technology? What do you see as the capabilities? And where do you see as the implementation?
So there's many possible applications across different segments of computing. It's really a general purpose computing architecture is a way to think about it, just a very different one from our conventional style. So, you can find applications at the edge, and all the way to the most lowest level sensory processing, like we've been talking about, odor detection, at very low power levels, battery operated devices that could be distributed. Uh, to more intelligent processes at the edge. So robotics is one where we see a lot of promise. Now, robotics is another one where there's the compute is not the only problem there. There's of course all the manufacturing and the mechanical aspects which have to be cheaper and more robust. But neuromorphic control is very, very well suited for that problem. That is basically why brains evolved, is to control bodies and limbs and articulate things. So that's an area where you're processing real world input, from whatever sensor modality you have. You need to make real time decisions about how to move or respond, and that's what brains are good at, and that's what this architecture is really good at. So we could see this going into, for example, manufacturing setting. That's where robotics has taken off so far, and so we could see neuromorphic chips processing data more adaptably, more faster in real time, which would allow us to just have more productive assembly lines. Defect detection, and being able to screen and monitor all parts, as opposed to in real time, as opposed to just sampled parts. would boost quality and productivity of our factories.
Very, very, very interesting. Yeah, absolutely. Well, I just want to thank you for being on with us. I'm going to shut down the video portion right now and I'll continue with you on the audio portion. Thank you so much. This has been Mike Davies from Intel and really appreciate being with us.
Sure, my pleasure.